Okay, let's debrief the problem that we had at the beginning of class, or at the end of class rather, and we didn't have the chance to debrief in class itself. So the issue here is, or the question here is, we have a ball that we're going to toss up with a certain speed that I call v0. The ball is going to travel up to a high point, 30 meters above the earth. It's going to stop. It's going to fall back down to the earth. What I want to do, and what we did is we split the group up, and half of the people solved for the time it takes to go up and the time it takes to come back down. And, well, one half solved for the time up and one half solved for the initial velocity up. And then the other half of the people solved for how long does it take the ball to come back down, and they found the velocity just before it hit the ground. So I labeled my velocities v0, v1, and v2. This velocity is the initial velocity of time up, and this velocity is the final velocity for the upward trajectory. But then on the way down, this velocity becomes the initial velocity for the ball going down, and v2 becomes the final velocity for the ball coming down. So this is a two-part problem. Well, we're making it be a two-part problem. So the up part and the down part. Okay, and again, the ball traveled a distance of 30 meters above the earth, which means that the delta x from going up was positive 30, and delta x coming down will be negative 30. Okay, so let's solve the problem. First of all, looking at the up, the time up and the initial velocity up. Okay, so let's look at up first of all. All right, so I have my equations over here. You can see the equations. And what we're trying to find is one of these two things. So let's see here. What do we know is true about all of these equations, the kinematic equations? Well, we know that v initial, the initial velocity, which in this case is v0, is in every single one. So I think that's probably the first ones we need to figure out. Now we don't know time, so what equation are we going to use? We're going to use this last equation because it does not have time in it. Okay, so let's write down what we know. We know that v initial for the up motion, that's what we're looking for. We don't know that. We know the delta x for up is 30 meters positive. We know that the final velocity, which is going to be the velocity at the very top, we know that at the very top it has to stop, so the final velocity is 0. And we know that the acceleration, because we're in free fall, right? The ball is freely falling, even though it's going up, it's still falling, is negative 9.8 meters per second squared. Okay? And a lot of people have a hard time with this. Why is it going up? Why is the velocity up when the acceleration is down? Okay, and remember, when the velocity and the acceleration are in the opposite direction, what does that mean? That means that the object slows down. Always. Okay, and does the ball slow down when it travels upwards? Yes, of course. So this is correct. The velocity is up and the acceleration is down. All right, so how are we going to solve this guy? So let's see here. We know we have to get the initial velocity, so and we don't have the acceleration. So what do we say? We set the fourth equation. Okay. Zeros are our friend. Anytime we see a zero, anytime we have a zero, we want to get rid of that term immediately. So v final is 0. Let's just go ahead and take care of that. So 0 is equal to 2a delta x plus vi squared. Okay, now I'm going to continue to solve this with variables. I'm going to do my algebra with variables. So I want to get vi, that's what we're looking for. I want to get vi by itself. Okay. So I need to subtract this whole thing over. Okay, and if it takes you a couple of steps to do that, then that's fine. But this should be a good final answer. Okay, and now how do we get vi? Well, we're going to take the square root of both sides. And some of you are thinking, oh no, how can we take the square root of a negative? Oops, sorry, it's just vi. All right, so in physics we like to write what the thing is that you're solving for on the left, and so I'm just going to swap those two. So how can we take the square root of a negative? Well, it turns out we're not. Negative 2 times A. What is A? A is negative 9.8, and make sure we put in units, meters per second squared, times delta x. And notice how I put my meters on the top and seconds squared on the bottom. A lot of people write it like this. And it's difficult to see what goes on top and what goes on the bottom, so I would write it like this instead. Okay, that's just a little aside, just a little thought for you. Meters per second squared times delta x, 30 meters. Okay, and notice what happens is when I multiply 9.8 meters by 30 meters and divide by second squared, I'm going to get meters squared over second squared. And then when we take the square root, we're going to get meters per second, which is what we should get. Okay, so I don't know what kind of calculator you guys have. I can show you how I would do it myself. I would just go ahead and plug in the square root symbol, and then this is minus here. This is the minus negative 2. So negative 2. A lot of people think it's the minus sign, but it's negative. So minus 2 times negative 9.8 times 30. Okay, and we are done. All right, and so this initial velocity we see is 24.2, we'll call it 25 meters per second. So that's my initial velocity, okay, on the way up. Some of you might have done it this way. You might have said minus 2 times negative 9.8 times 30, and then you got that answer, and then you took the square root of it. Let me show you how to do that easily on this kind of calculator. You do second square root, and then you do second answer, and that pulls up the answer from the previous line, and so you get the same result there and there. Okay, so that gives us the initial velocity on the way up. Cool. Now we can find time. So now that we know the initial velocity and we know the delta x, we know v final, and we know a, the only thing we don't know is time, so we can use any of these. Maybe the first equation may be the easiest to find time. So to find time, v final is equal to at plus vi. Okay, and I'm solving this guy for t. Again, v final is 0, so I'm just going to go ahead and make that guy go to 0. Again, we're on our way up. So this becomes 0 is equal to at plus vi. I'm looking for t. T is what I'm looking for, so I'm going to try to isolate t, which means I need to keep that term together for a while and then move this term over. How do I undo addition? It's subtraction. Okay, and now how do I get rid of the a so that t is all by itself? We have to divide. How do we undo multiplication? We divide. And again, we like to write it like this in science. Okay, and so, oh no, how can time be negative? All right, fear not. We take our vi, which is positive 24.25 meters per second, and we're going to divide that by negative, oops, sorry, I forgot that negative sign, negative there, minus 9.8 meters per second squared. Okay, and what is a meter per second squared divided by meters? I'm sorry, what is a meter per second divided by meter per second squared? It's just a second. So now when we plug this in, 24.25 divided by negative 9.8, we get a positive 2.47 seconds. All right, so that is our time. That's the time it takes to go up. And this is the velocity it had when it left the ground. All righty? Okay, perfect. So let's do the same thing coming down. Let's write down what we know. On the way down, now it's this part. Okay, so we know that vi is equal to 0. We know that delta x is equal to minus 30 meters because it's coming down, and we know that a is equal to negative 9.8 meters per second squared. Again, we're in free fall. All right, so what do we want to find first? Let's find, maybe we can find the final velocity, v2. Okay, so what is the final velocity? Let's look for that first. Well, what do we know? We know this last equation maybe is another good one to use as well. Okay, so let's do that first. Right? And what can we get rid of? We can get rid of VI because on the way down, the initial velocity was 0. And so this is going to be a much easier calculation. 2 times A times delta x, right? And now we plug in our numbers. A is negative 9.8 meters per second squared times negative 30 meters. See how those two negatives are going to cancel out? That's going to be nice. Okay. And when we do it, well, we've already done it. We can do it again. 2 times negative 9.8 times negative 30 is 24.25 meters per second. We have to be careful. This is the square root, right? So, for example, what's the square root of 16? A lot of people say the square root of 16 is 4, but it's not. It's plus and minus 4. So this is plus and minus, plus and minus. So which one do we choose? Is it plus or is it minus? Or which way is the ball going on the way down when just before it hits the ground? It's going down. So we would say this is negative 24.5. But at this stage in the game, don't worry too much about that negative. Let's take a look at the magnitudes. The velocity coming when it hits the ground is 24.25, and the velocity when it left the ground is 24.25. Oh my goodness, they're the same. And that is not an accident. That is actually what the physics tells us happens. Okay, well, let's figure out the time. All right, now that we know the final velocity, maybe the easiest thing to do is to play with this guy. Or if we don't want to use that, we could use any equation, but let's just do it. V final is equal to AT plus VI. Okay, and so again, the initial velocity is 0, so we can make that guy go away right away. We can solve this guy for time. And the final velocity we say is this guy, minus 24.25 meters per second divided by okay. And if we take 24.25 divided by we'll do it right, negative 24.25 divided by negative 9.8, we get 2.47 seconds. So it takes the ball 2.47 seconds to fall down, and it took 2.47 seconds for the ball to go up. So that gives us a lot of cool information. The ball going up and the ball coming down have the same time if they are launched from the same position and land in the same position. Okay? So if it goes up 30 meters and then down 30 meters, the time up is equal to the time down. The same is true with the velocities. The initial velocity going up, the velocity of the ball gets kicked upwards is the same velocity that it has when it hits the ground. Okay. Now this assumes no air resistance. If there were air resistance, then the ball coming down would have a slower velocity than the ball leaving the ground. But we pretend like there's no air resistance. So another way to think about this is if you shoot a gun straight upwards. Okay. It has the velocity of that bullet coming out of the gun is very, very, very fast, right? The velocity that the bullet has when it lands would be the same if, again, we ignore air friction, which on the Earth we can't ignore. But if you were on the moon and you shot a gun straight up, all right, the velocity that bullet has when it hits the ground will be the same velocity as if you just turned the gun straight down and shot it. Okay? So that's the implication here, and it's kind of a cool one. All right, thanks.